Hello, I'm Zackary from the Hong Kong Polytechnic University. I'm here today to present a work, Tracking Stuffed Toy for Naturally Mapped Interactive Play via Soft Pose Estimator. Our work is about how to enable a stuffed toy as a controller for interactive play. As you can see here, I'm able to manipulate the toy to interact with the dollhouse. This presentation is divided into 4 sections. Let us first begin with our theoretical groundwork. We enjoy extended reality because it can transport us to another world. Gibson defines its feeling, presence, as a sense of being in an environment. And if an existing system is immersive, it will induce presence in the users. Cummings and Bellison decompose immersion into 8 features such as image quality, field of view, and tracking level, among which they found that tracking level is the most important immersive feature. It refers to the number and types of degree of freedoms tracked. Naturally Mapped Control Interface, NMCI, refer to controllers that look and feel like the in-game object. They can be categorized into 4 categories. With good natural mapping, a user can instinctively map real-world action to an in-game action. Hence, NMCI is expected to enhance presence in the user. From here, we can see that the theoretical frameworks of XR and NMCI overlaps. Specifically, we now know that NMCI can enhance presence, while an XR experience ultimately aims to enhance the user's presence. Further, we also know that a high degree of freedom tracking is beneficial to presence as well. To visualize the joint perspective of XR and NMCI, we present a XR NMCI visualization cube which uses XR, natural mapping, and controller rigidity as orthogonal dimensions. With this cube, we can see that there are research gaps when we consider XR and non-rigidity dimensions. Particularly interesting to our case is that it indicates to us a research gap for a free-form NMCI controller for XR, or FNMCI. Our paper aims to explore the possibility of such controller via stuffed toys as people already know how to play with them. To investigate a stuffed toy controller, we aim to address 2 research questions. We need to first know how to track a toy. So we ask RQ1, is it possible to track a deformable stuffed toy for interactive play? Then we need to know how user will respond to this tracked toy. So we ask RQ2, how do players respond to this playable stuffed toy controller? First, we move to address RQ1. Tracking a stuffed toy requires tracking both the pose and deformation of the toy, which we call soft pose. Our idea on how to track a stuffed toy's soft pose is to combine pose estimation with cage-based deformation. We call our network Soft Pose Estimator. To prepare a dataset for training, we use synthetic dataset for practicality. We now talk about the Soft Pose Estimator's pipeline. The RGB input is first used to extract the feature and detect the bounding box of the soft object. We took a bounding square and then use ROI line to get the localized deep feature. Then, our network estimates the segmentation and normalized object coordinate, or NOC, to aid in the pose estimation. The segment mask is then applied to the deep features. Finally, the soft pose estimator estimates the pose and deformation of the soft object. Note that our regression network is trained with synthetic data but can be used for real RGB input. Here, we show the stuffed toys 3D reconstructions in cages. These are toys that are used in the study. From left to right, they are Pikachu, Penguin, and Dragon. To enable gameplay with the trackable toy, action recognition and collision detection are important to consider. By placing key points, we can use each of them for collision detection. Or, we can use the relations between them for action recognition with thresholding. To check the accuracy of our model, we manually label segmentation masks and use them upon the depth maps captured by Azure Connect. This provides us with a ground truth depth map. Here, we show some qualitative tracking results for the Penguin, Pikachu, and Dragon stuffed toys. With workable, trackable stuffed toys, we address RQ2 by conducting 2 user studies on how players will respond to them. For the first user study, we have recruited 15 participants. The first MR game is Pikachu at Home. In this game, the user will need to use the Pikachu to interact with the environment. The other MR game is Penguin in the Run. The user needs to avoid obstacles with the penguin by moving it around. The NASA TLX scores reveal that gameplay with the trackable toy is comparable to other video games. The partial CSI scales show that the gameplay is quite engaging and immersive. For the second user study involving an AR, we have recruited 10 participants. And for the AR device, we have used a video see-through HMD. In this second study, we are more interested in comparing the tracked toy with common controlling methods. Here particularly, we compare the tangible toy controller with hand tracking and typical joystick control. These 2 controlling methods are enabled by Oculus Quest 2. The second user study involves an AR game called Dragon Dungeon Escape, where the player needs to solve a simple room puzzle to free the dragon. The NASA TLX scores reveal that the tracking toy is a competitive mode of interaction with workload that is comparable to other common controlling methods. And the partial CSI scale show that the stuffed toy tracking seems to have an advantage in terms of engagement and immersion. Users also generally rank our trackable toy as the most preferred controlling methods for the AR game. Here are some of the excerpts from our focus group discussions which reveal some qualitative insights. To conclude, our work investigated how to utilize stuffed toys for interactive play. For further details, please refer to our paper. Thank you very much.